Sorry for all the issues. So yeah, let's start. Today we'll solve some problems related to week two's assignment from last year and like this year's practice assignment as well. So we won't solve week one's assignment yet because the deadline is tomorrow, right?
Okay.
Yeah. Okay, so let's start. The first problem is uh, which of the following choices will resolve the P versus NP problem and select all that apply. The options are a polynomial time algorithm for three coloring, a polynomial time algorithm for two coloring, a proof showing that 3SAT does not have a polynomial time algorithm, and a proof showing that 2SAT does not have a polynomial time algorithm. So, which of the options are correct?
So I think correct options are A and C.
Yeah. A polynomial time algorithm for three coloring, yes, and C, yeah. Yes, and the reason is that three coloring is NP complete. So
Yes.
if you have an if you have a polynomial time algorithm for coloring, you also get a polynomial time algorithm for every problem in NP, and so NP is contained in P, and so that would mean that P equals NP. On the other hand, a proof showing that 3SAT does not have a polynomial time algorithm would mean that there exists at least one problem in NP for which we do not have a polynomial time algorithm. That is, there exists a problem in NP which is not in P, and so P not equals NP. So A and C would work. What about B? We already know that two coloring is in P, and we do not know that it's NP complete. So a polynomial time algorithm for two coloring is known, and that does not give us anything. And the last statement is actually false. So we know that 2SAT is in P, and we have a polynomial time algorithm for that. So we cannot show that 2SAT does not have a polynomial time algorithm. So the only correct options are A and C.
Yes.
Yeah. Okay, so now let's look at the next problem. So the next problem is consider the following language, quadruple stat, which is defined as the set of all Boolean formulas phi such that phi has at least four satisfying assignments. And which of the following options is correct? The options are quadruple set is in P. Option B is quadruple set is in NP, but it is not known to be in P. Option C is quadruple set is NP complete. And option D is quadruple set is not known to be NP. So, which of these are correct?
Yes. So uh, uh, I think that D is correct. It is not known to be in NP because here we require two things. Not only we require an assignment, but we
Okay,
also require that the count should be greater than four.
right. Okay, so, but we can do the following, right? Instead of just providing one assignment, we can provide four assignments. And that means that
Mm.
the count is at least four, right?
Yes, yes, yes.
Yeah, okay.
So in that case, clearly the option B would be correct,
Yeah, B is
and
correct.
C would be correct, and then B and C would be correct then.
Yeah, okay. So, and why is C correct? So, B is
Uh,
clear.
yeah.
Why is C immediately correct?
So since we are looking for four satisfying assignments, so this problem would be at least as hard as a satisfiability problem is, and satisfiability is NP complete, so therefore this is also NP
Yeah,
complete.
yeah. So that intuition is correct. Yeah. So now let's just see how to formalize that intuition. So let me just because I'll just define L to be quadruple set to yeah, so that I don't have to write quadruple set all over again in multiple times in the proof.
Yeah.
Yeah. So first, let's just prove that it's an NP. The proof is just this. uh, given a formula phi and x1 to x4 in 0, comma 1 to the n. I'll assume that phi is an n-varied formula. Uh, we can check in polytime if phi of xi is true for all I in 4. Uh, if phi is in L, then such x1 to x4 exist. Yes, so if phi is in L, then there at least at least four such assignments would exist, so we are fine. And if phi is not in L, then at most three assignments would exist, right? Yeah. So this means that the an algorithm which just sees if x1 to x4, if I evaluated x1 to x4 is true, uh, does have the property that it only accepts phi which are in L and rejects all phi's that are not in L. So we do have a polynomial time algorithm for this problem. So polynomial time verifier for this problem. And so L is in NP.
Yes, so is this
Yeah,
necessary to show that for phi is not the element of the language?
right.
Uh, there are at most three satisfying assignments. So do we really need to write this thing explicitly for the no instances as well?
Okay, so suppose that phi were not in L, but your algorithm still accepted uh, phi, comma x1 to x4 for some x1 to x4, right? Then your
Mhm.
algorithm would also be accepting false, like the formulas which it should not accept, right? So the algorithm should do two things, right? It should accept formulas that are in the language and it should reject formulas which are not in the language, right?
Mhm. Mhm.
Yeah, so both are required.
Okay. Okay.
Yeah. Okay, so and the next thing is L is NP hard. Yeah, so if we prove this, then L would be NP complete because it's already in NP. Okay, so the proof is by reduction from three sat. So let phi be a three sat instance. Uh, define, okay, let three sat instance and suppose phi is the formula in variables x1 to x7. Create phi prime as, okay, so okay, so like would you like to guess how we would create phi prime?
Uh,
So if
yes.
there is one assignment, we want to make it that one assignment four assignments.
Mhm.
Yeah, so like would you like to guess how we can do that?
Yeah, difficult to guess.
Yeah, okay. Yeah, so it's this phi, and you add two new variables, x n plus 1 and x n plus 2. So you add two new variables and these two clauses. Okay, and clearly we can create phi prime. So we can create phi prime in polynomial type. So this reduction is at least polynomial type. Now we need to show that it's a valid reduction. So for that we need to prove that if phi is in 3 sat, then phi prime is in quadruple sat. Okay. So if phi is in 3 sat, implies that there exists a1 to an such that uh, phi of a1 to an, this is 1, right? Then uh, a1 to an and is a set of satisfying assignments. Of phi prime. Okay, so we can pick any assignment a1 to a, and for xn plus 1 and xn plus 2, we can put 0 or 1, doesn't matter, because this clause is always correct, right?
Yes.
Yeah, so in this way we can convert one assignment for phi into four assignments for phi prime, right?
Yes. Yes.
Yeah. So now is it clear why we added these two?
Yes, to
Yeah,
include four more variables. Because if we have one solution, so basically from one solution we are creating four solutions.
right. So suppose we wanted to create eight solutions. In that case, what would we have done?
Could not hear you. Can
So
can you please say it
okay, yeah.
again?
If instead of four, if instead of creating four assignments, we wanted to create eight assignments,
Eight assignments. Okay, so
right?
in that case, we'll have to include two more tautologies, and or few more
Okay, fine.
tautologies.
Why two more?
Because see,
Just one more,
tautology.
right?
Uh, so we'll have to include few more tautologies here.
Yeah.
Uh,
How many? How many more?
okay. So 2 plus 2 4, and okay.
Oh,
So
is it plus or is it multiply? So pick any satisfying assignment. Oh, pick any satisfying assignment of this
yes,
and any satisfying assignment of this. Like both of them. Like okay, so let's say 0, 1 over here. You have 0, 1 over here. Any
I
matching would give you
yes,
satisfying assignment, right?
yes,
So
I understood. So we'll
right,
have to include one more tuple.
right, yeah. We'll just have to include this
Yes,
n
it's
plus
10 plus 3.
3, n plus 3 complement.
Yes, it's a
Yeah,
very good point. Yeah, yeah,
yeah.
correct.
Okay, so this shows one part, right? If phi is in 3 sat, then phi prime is in L. We also need to show the other part, right? So
Hmm,
phi is not in 3. Okay, so we need to show that phi prime is not in L. Sorry, phi
hmm,
prime is in L implies phi is in 3 sat. But we can also show the contrapositive of it, which is like if phi is not in 3 sat, then phi prime is not in L, right?
hmm.
Wait, do I want to show the contrapositive of it? Yeah, I can. Let me just do it like this. So suppose phi prime is in L implies phi is in 3 side. So pick any A1 to N plus 2 such that phi prime of A1 N plus 2 is equal to 1. At least for such A1 to AN will exist, right? So with there are guaranteed to exist at least 4 satisfying assignments. Pick any one of them. Oh, this should be plus 2, not AN. Then uh, phi of A1 to AN is 1. Why? Because AN plus 1 and AN plus 2 are for these two clauses. But if phi prime is true at A1 to AN plus 2, that means that this, which does not contain xn plus 1 or xn plus 2, must also be true, right? But since this only contains x1 to xn, phi evaluated at A1 to AN must be true. Is this fine?
Yes, I don't know why, but your voice is not that clear, so I could not understand.
Okay.
Uh, there is some issue.
Well, let me try to reconnect, see if that's.
You may increase volume level also if possible.
I mean, I can increase. I don't know if I can increase my microphone's volume.
I could hear till that point wherein you said that this time you require an plus 1 and an plus 2 also, apart from say a1 till an.
Okay, okay, yeah. Okay. So, okay, so since phi prime is in L, we
Hmm.
have at least 4 satisfying assignments, A1 to AN plus 2. Pick any one. Okay.
Hmm.
Now, since phi prime is true at A1 to AN plus 2, phi must also be true at A1 to up to AN plus 2, right? Because if
Yes,
phi were false, then since there is an and over here, phi prime would be false, right?
yes,
But since phi does not contain xn plus 1 and xn plus 2, phi at an plus 1 to an plus, okay, let me write it. Uh, so phi of a1 up to an plus 2 is equal to phi of a1 up to an because phi does not contain xn plus 1 and xn plus 2, right? So
yes.
whether you plug them in or don't plug them in doesn't matter, right?
Hmm.
So this must be true. And so phi of a1 plus an must also be true. Is this fine?
Yes. So again, there is some audio issue.
Okay,
Uh,
let me try to like is my volume too low or is my voice breaking?
Actually, some echo is coming along with your voice. Not that
Okay,
not that harsh, but then still as if
okay,
you are sitting in some empty room. So along with your voice, something else
okay,
is also coming. So what you can do that you can also write something here. Yeah. So since I could understand that we do not know anything about the an and an plus 2, but since phi prime is the element of the language,
right.
so uh, yeah, so then phi of a1 till an should be equals to 1.
Okay, yeah. So, okay, let me just expand that. Okay, and by the way, for the echo, can you try muting yourself and see if there is still echo?
Yes, yes, yes.
Yeah. Okay, so let me complete this sentence and then I can ask you whether there is echo or not. So, okay, so since phi prime is true at a1 to an plus 2, phi has to be true at a1 to an plus 2 because phi is contained in phi prime. So, but since phi does not have the variables xn plus 1 and xn plus 2, uh, is not contained. So, phi of a1 to an plus 2 is the same as phi of a1 to an. And so a1 to an is a satisfying assignment. And this means that phi is in 3 sat. Okay, so first, was there still echo? And second, is this clear now?
So the solution part is clear, and
Yeah.
I could hear, but still echo is there, but not, but there is an improvement. I don't know. Is it same with the other participant also?
Oh, okay.
If she would like to
What?
comment, there could be an issue from my side also. I don't know.
Okay. Is the echo better now?
Yes, yes. I can hear you. Yeah,
Okay, so I changed my mic. Let's see if this is better.
sure.
Yeah. Okay, yeah. So that proves that L is NP hard, and since L is already in NP, yeah, L is NP complete. Is this fine?
Yes.
Yeah. Okay, so now let's look at the third problem. Because the next two problems are just recall problems. There is nothing much to explain. The problem is, what is the dimension of the valid windows that are checked in the proof of the Cook-Levin theorem? The options are 1 cross 3, 2 cross 2, 2 cross 3, 3 cross 1, 3 cross 2, and 3 cross 3. So which of this is correct?
C is correct.
Yeah,
2
C
into
is
3.
correct. And okay, so the next problem is also about that. Consider the computation table that is used in the proof of Cook-Levin theorem. If a table represents a valid computation, then how many states can appear in a row? The options are 0, 1, 2, 3 or more, and could be any integer. So which of these is correct?
So option B is correct, that there could be only one
Yeah,
state in the row.
yeah, that's true. Okay, so the next problem is consider the language shortest path. And this is the like so the four tuple G S T K such that G is an undirected graph and the shortest path from S to T is of length at most k. The set of all such four tuples is the language. And which of the following choices is or are correct? And select all that apply. So the options are shortest path is in P. It is in NP but not known to be in P. It is NP complete and shortest path is not known to be in NP. So which of uh, these are correct?
So here we need to find the shortest path, which is fine. The
Right.
solution is there in P, but then this path has to be of the length at most K. If it is the case of at least K, how will this make a difference? So here the question is of at most K.
Right.
Uh, so
Actually, in this
since
case, it won't matter whether it's at least k or at most k because all
because
you do is
Yeah. So
What
I
you do
think
is,
that the option.
right.
Yeah, please continue. Yeah.
Yeah. So,
So
yeah, go on. You were saying something?
yeah. If it doesn't make a difference, then the option A is correct that it is in P.
Yeah. Okay. Yeah. So option A is correct. And okay, let's see why it does not make a difference. So forget, okay, for now, forget about this part. Okay. Just let's find the shortest path from S to T. Okay. I lost network. Hello.
Yes.
Yeah, I lost connection. Can you
Yeah.
hear me now? Okay. Why isn't this shared? Okay, yeah. My screen is also visible, right?
Yes.
Yeah, okay. Yeah, so, okay, so I was talking about why it doesn't matter, why this is at most or at least. The reason is the following. All you have to do is find the shortest path. Okay, then look at the length of the shortest path. And whether it is, regardless of whether this is at most or at least, you can just look, check once you have found the shortest path, check if the length is at most k, say yes. And if this were at least, check if the length is at least k and say yes. So the main part over here is not whether the length is at least k or at most k, it's just finding the shortest path.
Yes.
Yeah. So in this question, it doesn't matter.
Yes. Yes.
Yeah. But in the next one, it will. Okay. So the next is consider the problem longest path. And this language is the set of all four tuples G, S, T, K, such that G is an undirected graph with and the longest path from S to T is of length at least K.
Hmm.
And the options are longest path is in P, longest path is NP but not known to be in P, longest path is NP complete, and longest path is not known to be in NP. So which of these are correct?
So I think correct options are B and C. The longest path problem is in NP and
Yeah,
uh, it's NP complete as well.
right. Yeah, and over here, at least matters. If it were at most, then this would I think be in co-NP and maybe even co-NP complete. Yeah.
Mhm.
Okay. So let's first see why this is an NP. So yeah, again, I'll just define them to be longest path.
So just wanted to remind you in
Yeah.
case you forgot to record this session that you are not
No, I'm
recording it.
recording. Yeah, I'm recording it. Yeah.
Okay, all right, yeah.
Yeah, so for some reason, I'm not able to record in the Gmeet, Google Meet, so I'm recording using an external software. Yeah.
Okay, yeah, fine.
Yeah. So L is, okay, yes, let's say L is the longest path, and then first, okay, so if, okay, uh, given GKST, okay, a sequence, we can easily check if the sequence is a valid S to T path, and uh, its length is polynomial time. Okay, so yeah, we can do this. And now if GSTK were in L and there exists such a sequence, why? Because this sequence can just be one of the parts of length at least k, and such a path should exist if GSTK is in L, and uh, if GSTK not in L, no such sequence exists. Yeah, so an algorithm that takes GSTK, a sequence of vertices, and just checks if that sequence is a valid path of length at least k, is a polynomial time very path for this language. Okay.
Yes.
Yeah. So so the language is in NP. Now about NP completeness. In this, yeah. So this is by reduction from Hamiltonian path. Okay. Yeah, I don't want to write n path again and again, so I'll just call it L prime. Okay. And so the reduction is as follows. Given an instance G of L prime create G prime as follows. Uh, the vertex set of G prime is the vertex set of G union two vertices S and the edge set of G prime is the edge set of G union is in VG union V comma T. Okay, so is the construction of G prime clear? So what we are doing is this. Let's say this is G. We're adding in two new vertices and connecting them with every vertex in G.
Yes.
Yeah. So this is what the
And if
construction.
yeah,
Yeah.
and if the Hamiltonian path exists,
Right.
then clearly that would be the longest path.
That along with two extra edges, right? From S
Yes,
to the first vertex and last vertex to T.
correct, correct,
Yeah. So and that path would have length n plus one. So we'll just set K to n plus one.
correct.
So now the instance of L would be G prime S T and n plus one. Okay. So now clearly the instance can be created in polynomial time, right? Yeah, so the instance can clearly be created in polynomial time. So this reduction is at least polynomial time. Now we need to show that it's a valid reduction. So for that, G in hand path implies G S A. Yeah, so you already mentioned how we can do this. Let me just write it. So there exists say V1 to V2 to up till Vn in G M mm, S to V1 to V2 Vn T is an ST path in G prime of length. Okay, so G prime, so this is true. Yeah. So this proves the forward direction. And what about the reverse direction? So Okay, yeah, let me call this, say that this is Q. Okay, so uh, since G prime is in L, there exists a path. Okay, let me call this path, say S to V1, V2 in G prime of length greater than equals to K equals to N plus 1, right? But then, okay, so if a path of length N plus 1 exists, then every vertex in G prime must appear on the path, right? Because G prime has at most as just N plus 2 vertices, which means that if you leave out S and T, all the other vertices, that is the vertices of G must appear on this path exactly once. And that means that V1 to V8 must be Hamiltonian path reducing. Is this fine?
So I have a doubt here that
Yeah,
here we are reducing Hamiltonian into the longest path problem.
right.
So it shows that each and every instance of the Hamiltonian can be rephrased as an instance of the longest path problem.
Yes.
And this reduction is a one-way reduction, and therefore we need not to show that if we have an instance of am I audible or
Yeah, you're audible.
are
Hello.
you still connected?
Yeah, you are audible.
I can't hear you. Yeah, can you hear me?
Yeah, I can hear you.
Could not hear you properly. Am I audible?
Yeah, you are audible.
Connect again. I think that you're not audible to me. So
Yeah.
am I audible to you?
Yes.
Yes. So we are reducing Hamiltonian to the longest path, and we are rephrasing each and every instance of the Hamiltonian as an instance of the longest path. So now,
Yeah.
is this second part necessary, wherein we are showing that if f of x exists, then x also exists, because the reduction is a one-way function, and it is not necessary that if A is going to be reduced into B, then we need to show that if the f of x exists, then x also exists.
Okay, no, 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 that is required because of this reason. Okay, I let me write it over here. Okay, so when we say that A reduces to being polynomial type, so what's the definition of this? Uh, there exists a polytime computable F such that for all x in okay, and this is equivalent to saying x in A implies f of x is in B and f of x is in B implies x is in A, right?
Yes, so yeah, then why do we used to say that this reduction is a one-way function?
Okay, first of all, what do you mean by a one-way function?
So the meaning of one way is that if clearly if A can be reduced into B, then it's not necessary that B can be reduced to A as well.
Okay, that is not a one-way function, right? That's a non-invertible function.
Hmm. Hmm.
Okay, so what a one-way, okay, the reason I'm saying that is because one-way function has a different meaning in cryptography and even in complexity theory.
Yeah, yeah, could not
Okay,
hear you. Can you say this statement again?
okay, so what I'm saying is if you cannot, so what you are saying is f is a non-invertible function, and the reason
Hmm.
I'm making a distinction between non-invertible and one-way is because one-way function is yeah, it's an entirely different concept in cryptography and complexity theory. It is
Yes, yes.
okay. So what we are saying is f is not an invertible function, and that is correct. Okay.
Mhm.
Okay. So
Okay,
then,
all right. Yeah, so yeah, perfect. And so do we also need to show that if X is not the element of A, then the F of X complement is not the element of B either?
yeah.
Do we need to
Okay. So
show this thing also?
right. So this is the definition of reduction, right? And over here, what you are saying is exactly the contrapositive of this, right? Okay. So
How?
okay. So the what would be the contrapositive of this? It would
So
be uh, the complement of this.
yes,
The complement of this implies the complement of this, right? And the
yes,
complement of this is x is not in A, f of x is not in B, right?
yes.
So we also need to show
Okay,
that.
okay, yeah, yeah. Okay,
Yeah.
okay.
And
So
okay,
since we have shown that fx is not either we can go for an alternative solution could be that we show that x is the element of A. This implies that f of x is the element of B,
yes,
and if x is not the element of A,
right.
then f of x complement is neither the element of B. That would be
Y-
equivalent to this thing that we are showing it in both the directions. Will
Right,
it be fine?
yes. Yeah. Because the second part is the contrapositive of this.
Yes, yes, I
Yeah,
understood. Yeah,
yeah,
that's a very good point. Yeah, thanks.
right.
Yeah, clear.
Yeah, I've seen a lot of people with this doubt that, yeah, why do we need to show the other direction?
Yes.
Yeah.
Yeah.
Okay, so then, okay, so that also proves that L is NP hard and it was already in NP, so it's NP complete. Is this fine?
Yes.
Yeah. Okay, so now let's move on to the next problem. The next problem is which of the following languages are CoNP complete and select all that are CoNP complete. The options are SAT, SAT complement, tautology, and clique. So which of these are correct?
B and C, I think
Yeah,
the complement of set and the tautology.
yeah. Okay, so was this covered in class
So I read this thing from the notes. So
from the
might
class notes?
yes, yes.
Okay, yeah, because yeah, so if it's covered in the class, I won't cover these two reductions.
But still, it would be really helpful if you can show that the complement of set is there in the NP.
Okay, so let me do
Yeah,
something.
hello, can you hear me?
Yeah, yeah, I can hear you.
Yeah, I have actually some very basic doubt about co-NP. So,
Okay.
okay, this is quite stupid. This is quite a stupid doubt, but I'll go ahead. So the thing is ki I'm thinking, why is NP not closed under complementation? Because like
Okay. You want to flip the answer, right?
exactly,
Yeah, okay. Okay. So what you want to do is the following. You have a non-deterministic Turing machine.
right.
If it accepts, you want to reject, and if it rejects, you want to accept, right?
No, no, no. That's not what I'm saying.
Okay.
Yeah, I know that won't work because
Okay.
yeah, I know that that doesn't work. But so actually, it's a very fundamental doubt about non-deterministic. So how does an when non-deterministic Turing machine accepts uh, when do we say a language is in NP? When there exists a non-deterministic Turing machine that um, that accepts that accepts every element of it. That means ki there is a path from that there is a
Right.
path such that it goes into an accepting state. Otherwise, it rejects. Right.
Right.
So if so, why can't I say ki uh, why can't I do ki if it is, yeah, exactly. Why can't I do
Okay.
if it's
So
accepting reject?
yeah, let me write this. L is in co-NP.
Actually, I'm sort of confused about non-deterministic Turing machines itself.
Yeah. Okay. So okay. Uh, so what you are saying is this, right? L is in NP if there exists polytime uh, non-deterministic Turing machine n such that for all x in L, uh, nx accepts. Okay, let me write this as one. Nx outputs one, so nx accepts, and for all x not in L, nx equals to 0, right? So this is the definition of NP. Okay. Now,
Yes, yes.
okay. So now, what does this mean? What does this statement mean? Okay, I don't have space. There exists an accepting path in n on input x, right? And uh, for no path, or okay, all paths in n on input x are rejecting paths. Okay, so once we have this, now what's your doubt?
Yeah. So my doubt is that yeah, let's say the Turing machine gives one. I'll just
Okay,
output zero instead, and if
okay,
it
right.
outputs, yeah. So
So
does that
wait,
so
that
does
is
that not
what
give
I
us the
mentioned
language?
first, right? So
Yeah,
that
yeah,
was
yeah,
okay. Okay, so it's exactly the same, right?
yeah, yeah, yeah.
Okay, yeah. Okay, so what you want to do is create another Turing machine n prime which does this. You want to do this, right?
Yes, yes, exactly.
Okay. Okay, so now let's see what this means. This means that n prime x uh, n prime x is equal to 1 implies, okay, if and only if nx equals to 0 and this, okay, by the way, this is these two are if and only ifs. So if and only if all paths in n on input x are rejecting, right? So this thing over here. Okay, so all paths in n on input x are rejecting paths. And what does that mean over here? Okay, so is this fine?
Yes.
So,
So what
yeah,
this tells us is that n prime x is 1 if and only if all paths are accepting, right? But for NP, what we need is a much weaker condition, right? That exists an accepting path.
Right, right, right.
So what might happen is the following. For like, okay, so if you want to show that L is in NP, it is completely fine if some path rejects. As long as one path accepts, you must accept. But what n prime is doing is it's not doing that, right?
Right, right, right. I see, I
Yeah,
see.
yeah. Okay, so
so yeah, so last time also we had a discussion on this, and
right.
from this definition, it seems that a language is the element of NP if it is
Hmm,
uh, it is decidable by a non-deterministic Turing machine.
right.
So again, now today I am unable to convince myself that do we really need to consider the no instance? And I would be really happy if you can spend some 2 minutes time on this
Okay,
document.
okay,
The link is there in the chat, and you please read this definition of NP from this document and
okay, yeah.
let me know that do we really need to consider no instance while proving that the language is the element of NP.
Okay. This document is taking too much time to open. Let me reload it. Okay, so uh,
Uh,
okay,
so
can you put a screenshot of it in the chat? The definition?
okay.
Yeah.
I'll do that. I'll do that.
I mean, I can try to change my connection, but then I would lose this connection. I don't want to do that. I've already done those that twice.
How to paste
Oh,
this? How to share this
I don't know. Okay. Let me try to open it in my iPad. Let me see if that works. Okay, I'm going to open chat over here. Okay, for some. Okay, now I can.
Yes.
Okay, now it has opened at both places. Great. Okay, so is it like? Can you tell me a definition number?
Yes. So this is the very first definition, the
Okay,
remark of the
remark one.
definition of NP. Yeah.
Okay, a problem is in NP if and only if there is a polynomial time computable f in a polynomial time bound P such that x is a yes instance if and only if there exists y such that okay. So okay, what I'm doing is I'll just copy like I'll rewrite that one line over here. X is a yes instance. If and only if there exists y. Okay, I think there's some typo over here. 0, comma 1 size of x and f of x comma y. Okay, so the last statement is f of x comma y, right? But that's the same as f of x comma y equals 1, right?
Yes.
Okay. So let me go back to the definition of the reduction. So over here we had a if and only if we split it, right?
Yes.
Let's do the same thing over here, and that should clear the problem. Okay, so x is a yes instance, and I'll just copy. Okay, so x is a yes instance implies there exists this, right? So
Yes.
this was just one way. Okay, now what do you want me to do? Do you want me to write x is a no instance implies something, or do you want me to write this direction?
Okay. Okay. So fine. So now let us write in the direction wherein x is
Okay,
in no instance. So
okay,
if f of x y, okay,
okay. So you want me to write this, right?
yes.
Okay, so now what should I write over here? Can you tell me?
So yeah, nothing. Yeah. So if x is a no instance, then the complement of f. So that means that
Wait,
if
find the
x is
complement of f. Okay, let me do one thing. Let me first write this. There exists y
mhm,
in 0, comma 1 to the p.
right.
Okay,
Mhm.
so okay, now let's again exemplify. Okay, right? Yes, so we get this. And now what we'll do is we'll just uh, now we'll rewrite this second statement, the contrapositive of the second statement. Okay.
Mhm.
So what is the contrapositive of this statement? X
X is a
is
no instance
right implies.
for all
What's the
y.
negation of this?
For all y,
Right.
0 comma 1 polynomial in x or f of x y is equal to 0. So if you do not pay much attention to this for all y thing, then the f of x y should be equal to 0.
Wait, okay, but if you just forget about the first thing, then hold on. There exists y such that this. So for all y, no, no, wait, I think there is some issue. Okay, so there exists y f of y equals 1 for all y f of y equals 0. So there exists for, oh wait, there exists for all y, y is in this, or f of y is 0.
So I think that we should
No,
not
no,
take
no,
the
no.
literal meaning of the term and or here in this definition at least. So here, if x is a yes instance, then this simply says that there exists a value of y such that the f of xy is equal to 1. So we should not pay that much attention to this end here, which we are converting into an or
Yeah, but
after taking
yeah, but the
negation.
thing is, this definition is true. So what I'm wondering is why should we take it
Okay,
literally?
okay.
Why for all y? Ah, Okay, I see it. Let me, okay, so let me write the exact thing over here. I tried a shortcut that way. Yeah. So what the exact thing written over here is this, right? For all there exists y, such that, so the exact thing is this, right? Y appears twice, and that's important. I think, yeah. Okay, let's see. I need to replace this. Okay, so now we need to negate this, right? Yeah, this is a nice way. So this is the exact negation, right?
Yes.
Okay, now is it clear?
Yes,
So
yes,
what
it's
this is saying is this statement is exactly equal to this, right? Okay, I've been using this is exactly equal. Okay, no. Let me write it for the entire. So this is exactly the same, right?
yes, correct.
Yeah. So this full stop is so the okay. So separating two things. There exists why full stop. Why this is important.
Yes.
Yeah.
And it will be really helpful if you consider the definition of the co-NP as well, and which is given just below in this document
Okay.
after this NP.
Definition. Oh no. Yeah, X is a yes instance if and only if that thing, right? Let me write. X is a yes instance if and only if for. Okay. Now there is no. Okay. So how am I supposed to interpret this comma? Is it and for all y? Oh no. Wait. For all y this comma f of x, y. So I is in this. Okay, so I think what is written is this. Okay, so even before I go to co-NP, is it clear for NP why we need to consider both yes and no instances? Because that was the
Yes,
doubt, right?
yes, this is very much clear this time.
Yeah.
Yeah.
Okay, yeah. So we forgot that because we got lost in this formalism. Okay, so now let me write for co-NP. X is a yes instance. If and only if for all y such that y is in 0, comma 1 to the e of x of x, comma y. Yeah, and this is like saying f of x, comma y equals 1, right? Okay, so one direction is fine, the other would be an issue. Okay, so x is an, okay, yeah, let me just do it like this. For all y, copy. Okay, let me paste it. Okay, so now the first statement is fine. We need to look at the second statement, right? The contrapositive is x is a no instance. Implies a negation of this. There exists y such that y is in
Y is, yeah.
yeah. So this is the
So
negative.
what this comma here is, should we consider this as an and or what?
Oh,
Even though they have simply given a comma here,
yeah.
and
Exists y complement.
so let us consider and here, and if we
Yeah,
take its
okay.
negation, then it will become there exists y is not the element of this thing,
Hmm.
or the f of xy is equal to 0. And since we are only considering the witness of
Okay.
the polynomial length, so therefore the value of f of xy has to be 0, which will make sense, I think.
Okay, but my problem is with there exists. So there exists y
Such that y
such
is
that
not.
y is not.
No.
Oh, okay, okay, then okay. So there exists y so that y is not in this, or f
Yeah.
of xy is 0. And what
Yes.
does this mean? Why there exists y such that, okay, y is not in 0, comma 1 to the precise p side of x, or this. So y.
So I think that this
This is
this
always true, right? This statement is always true. No, no, because there always exists a y
yes.
which is not in this.
But then here to make
Okay,
this
then this has to be true, right?
yes.
Yeah, yeah, yeah. Okay, yeah. So if there exists, okay, so yeah, if you try to pick any y which satisfies this, no, but okay, so y is not in this. Okay, yeah, yeah, but this is always true, right? Because pick any y in 0, comma 1 to the px, this would always be satisfied. Forget about this.
So this y is not the element of 0 comma 1 and its polynomial is always false, because we are only considering the witness of the polynomial length.
Okay, no,
So
but
since
okay, where is this written in the definition? So okay, I agree. If you add that to the definition, then we are fine. But where is
yes,
that written in the definition?
so end is there, end is implicit in the definition, because it neither it says that, because it only says that for all y is element of this thing comma f of xy. So and they are not writing them, not writing it as say f of xy is equal to 1. So it shows that this comma here refers to end.
Yeah, okay, so I agree with that. But what I'm saying is, if you negate it with considering comma to be and, you get this, right?
Yes.
But the problem is,
And
I want this
so to
state,
make
okay,
this
I want
entire
this
thing
statement to
true,
be true, right?
yes,
So this says there exists y such that this or this, right? All
correct.
I'm going to do is pick a y in 0, pick a y not in 0, comma 1 to the px, then this is true. But such a y always exists, right?
Yes.
So I think you need to add one more thing over here. Okay, so for all y in this, that exists y in this. Okay, so I think what you need to do is this. Yeah, I think you need to replace this by this. For all y, f of x comma y equals to. because then if you if you negate this, what you would get, there exists y in this set such that f of x comma y equals 0, right?
Yes, yes, correct.
Yeah, so I think you need to get rid of this colon over here.
But then this colon makes sense here. It says that I mean
Yeah,
this is similar to the previous definition that for all y. So because then we will be having a chance to consider y, which is not the element of this. Because if you remove colon from here, then we will lose that opportunity.
no, no, okay, so we do it, right? So what we write is for all y in 0, comma 1 to the px. So now we are only considering y 0, comma 1 to the px.
But I think that this last line is correct as such. It simply says that there exists a y such that y is not the element of this thing, which is not true,
Okay,
which can never be true,
why?
because we are only considering the
Right,
witnesses
so
of the.
what I'm saying is
So
that
therefore,
would be
the
true
value of
if
x.
somewhere over here we were saying that y is in 0, comma 1 to the px, right? Okay, so you are saying that we are only considering y that is 0, comma 1 to the px, right? Where is that written in the definition? So okay,
I'm
so
able, your voice is breaking, but then I'm able to understand it. I do not find any flaw here. It simply says
okay.
that if you simplify this right hand side, it simply says that there exists a y for
Hmm.
which f of x y is equal to 0. That's it.
Okay, y. Okay, what I'm going to do is let me just take y is
Mhm.
equal to 0 to the p size of x plus 1. This is my y. And my claim is this y satisfies this.
Mhm.
So are you convinced that this y satisfies this? Because it satisfies this. So, okay, so what you are saying would be true if you had this one over here. So if I add this after there exists y, then what you are saying would be true.
Mhm. Uh, do you think that some modification is required here? Otherwise, I'm pretty happy with this definition and your explanation. I'm
Yeah,
able
okay,
to
so
understand this.
what I'm saying is in the definition, just remove. Okay, so there is for all y colon, right. What I'm saying is remove y, remove colon. For all y 0, 1 to the px, this. That's what I think it should be.
But can we ever have a value of y which is not polynomial? We can never
Yeah.
have this.
Okay, no, no. Okay, okay. So what about 0 repeated 2 to the n times?
So because I mean, we will only be considering the witnesses of the polynomial length. So
Right,
therefore,
that
there's
is true. That is what we
in
do. But what I'm saying is, in this statement, where are we forcing y to be of polynomial length?
yes, because this is implicit, because why has to be so either, I mean,
Right?
to make this entire right hand side true, one
Hmm.
of these two should be true. Either
Right?
y is non-polynomial
No,
or
no, no.
the
Okay,
f
no,
of
no, no.
x
Okay,
y.
no, no, no. This is not saying y is not polynomial. All this is saying is that y, the length of y is not this. I mean, there can be other polynomials, right? For example, consider p square size of x. So p is just one polynomial, right?
So if
Hello.
polynomial, so I can always replace this p square of x by say t of x, perfectly fine. And t is a function which can be computed in the polynomial time, because if
Okay.
p of x is polytime computable, so is p square of x,
Right. So
isn't it?
what I'm saying is, you are right. This statement only does not say that y is the length of y is not polynomial. All this statement says is that the length of y is not px. So okay, let me say that px equals n. Okay. And what this statement says is that the length of y is not n. It does not say that the length of pi is not n square, right? And n square is still polynomial.
Mhm, mhm,
Because over here, p is not any polynomial, any arbitrary polynomial. It's a very fixed polynomial, right?
mhm, mhm.
So all this says is that yeah, length of p is not p like p size of x. Yeah. So I am still not convinced that this would work. I think you need to change this. Right. There exists. Yeah. Oh. Okay, so let's do one thing. Let's go back to the problem because I don't see any way of resolving this. Okay, yeah. So at least the NP thing is clear, right? Hello?
Yes, yes, audible now.
Yeah.
Somehow, I lost last 2 3 minutes, but it's fine. We can continue to the next thing. Yeah, this
Okay, yeah.
explanation was very much intuitive and
Okay.
understandable. Thank you.
Okay, so I asked something about this question. Oh, okay, yeah, yeah. So what I was asking is, have you seen this in class or should I do the proof?
I don't know whether I am audible or not, but your voice is breaking. I am unable to hear you. Is it same with other participants? Can someone please confirm?
Yeah, so if
Is
my
this
voice
is,
is
is this a
breaking, I have to
problem at
change
my
my
end or
connection.
someone please?
Okay, let it. Okay, yeah. So I think I'm audible to the other two. Okay, so let me write what I was saying in the chat. Yeah, so for question 7, like, did you see this in class that these two languages are co-NP complete, or should I do a proof of that?
In future, this proof there that the comment of set is
Okay,
co-NP complete. Yeah.
your voice is breaking. Did you say the following? Can you do the proof of part B?
Yes. Yes.
Okay, okay. Okay, so what I'll do is let me do something more general. Let me do this. Let me prove that in which was what was the number 5. So I'll just prove this, and like once I prove this, what we can do is we can replace L by sat, and we are done, right?
Yes.
Okay. So first I need to prove that L prime is in co-NP, right? So L is in NP implies L is in co-NP, right? So this is clear. So now all I need to do is show that L bar is co-NP hard, right?
Yes.
Okay. So uh, L is NP complete. Mm, theoret exists. Uh, Polytime. Polytime computable F such that for all x in okay, I for all L prime in NP, I forgot this. Yeah, so this L is NP complete implies that every language in NP reduces to L, and this is exactly what it means to say that every language in NP reduces to L, right?
Yes.
Okay. So what does this mean? Okay, so now L prime P in co-NP. Okay, is it you know let A be in co-NP. Okay. Now what do I want to show that A reduces to L, right? So I want to show that A reduces to L complement, right? So put okay, so A is in co-NP, so A complement is in NP and set L prime equals to A complement, right? And what do I get? For all x in 0, comma 1 star x. So x in L prime is the same as x in A complement if and only if f of x is in L, right? And this is the same as is this fine?
Yes.
Yeah. Okay. So what do we have? We have a polytime computable f such that x is in A if and only if f of x is in L complement, right? But this
Mm.
means that A reduces to L complement, right? Now A is any arbitrary language in co-NP. So all languages in co-NP reduce to L complement, right?
Yes.
Yeah. And in fact, I think we saw something. Okay, so this second part showing that L is NP complete implies L bar is co-NP complete. That can be thought of as a special case of the following statement we saw last time. If A reduces to B, then A complement reduces to B complement.
Mhm.
Yeah.
Mhm.
So I mean, okay, try do. Okay, so instead of doing this explicitly, instead of doing this entire part, try proving this using that statement. That can also be done. Okay, but okay, forget about that. Is this reduction? Is this proof clear?
Yes, this is clear. Till here it is
Yeah,
clear.
yeah. So now all we need to do is put sat instead of L, and we are done for part B. Is this fine?
Yes. So we replace this uh, A by set. Sorry, not A by set, but then we
L.
need to replace.
Okay, okay, forget about the proof now. So this proof was to prove this claim, right?
Yes.
So if I replace L by stat,
Hmm.
then L complement would be set complement. And what does this say? Set complement is co-NP complete.
Yes.
That is what we want to prove, right?
Correct.
Yeah. Is this fine?
Yes. Yes. Very
Yeah.
much.
Okay, so then let's move on to the next problem. Okay, yeah. So the next problem is uh, assuming P not equals NP, which of the following languages are not NP complete? Select all the correct answers. The options are finding the minimum spanning tree of a weighted and directed graph, finding the maximum spanning tree of a weighted and directed graph, deciding if the given directed graph has a cycle, and deciding if the given directed graph is acyclic. So which of these problems are not NP complete if P not equals NP?
So if P is not equals to NP, then
Right,
the first problem, that the minimum spanning tree, which is of P class, won't be same as the NP class.
right.
So
Because
if yeah,
yeah, because minimum spanning tree is in P. And if minimum spanning tree were NP complete, then that would mean that P equals NP, right?
yes,
Yeah, so A is true. What about B?
finding the maximum spanning tree of a weighted.
Okay,
Not
so
that.
for now, but assume that you had an algorithm that
Mhm.
could find minimum spanning tree in a graph, even if the edge weights were negative. Suppose you had
Mhm.
such an algorithm. Then can you say something about B?
Okay, so getting the minimum spanning tree with the negative weights would be same as the
Hmm,
getting the maximum spanning tree for the positive weights.
exactly, yeah. So if you had such an algorithm, then this would work, right?
Yes.
Okay, but turns out there is a way to make this reduction work even when there are even if you don't have such an algorithm. Okay, so let me show why this is true. So max spanning tree. So what I want to claim is this, which claim is this? Max reduces to min spanning. So if we prove this, then B also would be true, right?
Mhm.
Okay, so what we'll do is, okay, okay, this is fine. Then T8, mm, G of P of G. weight in Okay, so here's what we are going to do. We are going to create a new graph. The edges and the vertices would be exactly the same. Yeah, okay, so someone in fact suggested this. Replace all weights with very large number minus weight of edge. And this is exactly what we are doing. We'll first find the W, which is larger than all edge weights. And that would suffice for in case of a very large number. And then, yeah, if the edge weight was WE, we will make it W minus WE. And now the weight, okay, let me put it like this. T is a spanning tree of weight uh, capital W in G if and only if T is a spanning tree. Okay, so can you tell me what should I write over here? What should be the weight of T in G prime?
What is the weights of T is a spanning tree of
NW minus W. N, sorry, N small w minus capital W.
Almost.
Yeah, yeah, yeah.
Yeah, because, okay, so let's see why. Okay, so what we have done is we have created G prime by replacing an edge with weight W with a weight W minus E, right? But the underlying structure of G and G prime are exactly the same. So if T is a spanning tree in G, T must be a spanning tree in G prime. Okay, now all we need to worry about are their weights. So suppose that the weight of T in G was W. That is the sum of all the edge weights was W, right? But now each and every edge has been replaced with a weight W minus that WE, right? So now the sum of all the edges in G prime would be n minus 1 W minus W because there are n minus 1 edges in any spanning tree, right? So is this statement fine? Okay, like is this fine or should I explain this again?
yes, because we have replaced every weight by the weight minus the sum of all the edges. But I could not understand that why are we using n minus 1 into w here? I missed something and I got
Okay,
disconnected in
okay.
between. So yeah.
Yeah, okay, so suppose T was okay, then W. Oh, wait. Okay, so suppose T contains even to En, then
Mhm.
W is this, right?
Yes.
Uh, A, okay, in G. So in G prime, the weights W minus WE, right?
Mm-hmm. And what this small w here is?
Okay, small. So it is some number which is greater than all edge weights, so that this number is positive.
Ah, I see. I
Yeah.
see. Right. Yeah.
Yeah. So then T and G prime. So what is this? This is W minus WE1, and this is like W plus
Yes. Now it's clear.
this is N minus 1 plus over.
Minus probably.
Oh, yeah, yeah, yeah. Yeah. So now this is clear, right?
Yes.
Okay, and what does this mean? If tree were a minimum spanning tree in G, then T must be a maximum spanning tree in G prime, right?
Yes.
Yeah, so all we have to do, oh, wait, I, or the other way around. Okay, sorry. So if T is the maximum spanning tree in G, that means that T must be a minimum spanning tree in G prime, right?
Mm-hmm. Mm-hmm.
So all I have to do is start with G, create G prime, and find a minimum spanning tree in G prime. That's it.
All we have to do is what?
Okay, so we are given G, right? From G, so we are given G from that. So from G, we construct G prime, and we find the minimum spanning tree in G prime. If that tree is T, then the maximum spanning tree of G would be T. So is this fine? Okay. Okay, let me write. Yeah, so this is the algorithm. So is this fine?
Yes. So from G we create G dash, find the minimum spanning tree in G dash, and output that tree, and that would be the maximum spanning tree. That G would be the maximum spanning tree
Yeah, that would be the maximum spanning tree in G.
in G. Right.
Yeah.
Right.
So that means this is true. Okay. What about C and D?
So deciding if the given directed graph has a cycle, what kind of a cycle?
Okay, so a graph is directed, so there is only just one type of cycle, right?
Okay.
These are both in P.
Yeah, both of them are in T, so these are also correct. Okay,
Yes.
so why is C in P? What if
Given
yeah,
given a cycle, I can verify.
yeah, that is true, but how
Yeah,
can
I
you
can.
tell me an algorithm to verify that?
Yeah, I will do a DFS on it, and
Yes. So all you have to
yeah,
do is do a DFS But yeah, while doing this DFS, just like pay heed to this that whenever you encounter a node and you check the visit, if the visit is already 1,
Yeah, yeah, yeah.
so is this clear why, how you can find a cycle in the directed graph using DFS?
Yes, yes.
Yeah. And okay, so then what about the last option?
Yeah, if I keep doing the DFS and I don't find at any point that visited is
Yeah,
true already, then yeah.
yeah. So basically, yeah, just by doing a DFS and checking if visit is 1 ever, you can solve both C and D. So both of them are in P. So all four are in P and all four of them are correct. Is this fine?
Yes, yes.
Yeah. Okay, so let's look at the next problem. Which of the following is or are currently known to be subsets of sigma 2p? The options are NP, co-NP, pi 2p, and sigma 3. So which of these are correct?
I think A and B are correct.
Yeah. Yeah, so we know that both of these are in sigma 2p. What about C and D?
So sigma 2 cannot be same as pi 2. We don't know.
Right, so if sigma 2 were equal to pi 2, the polynomial hierarchy would collapse to sigma 2, but we don't know that, right? So
Yes,
far, we don't know anything about sigma. We don't know whether sigma 2 equals to pi 2 or sigma 2 does not equals to pi 2, right?
yes,
So yeah, and same with D, right? If sigma 2
yes,
and sigma 3 were same, again, pH collapse.
yes.
Yeah. Consider the following two statements. Statement P, sigma 2 equals to pi 2 implies the pH collapses, and sigma 2 not equals pi 2 implies that pH does not collapse. So, which of these are correct? Only P, only Q, both, and none.
So I can only say that option A is clearly correct,
Yeah.
and I do not know about the statement Q whether it's correct or not.
Okay, so Q is false, and here's the very simple reason. Suppose, okay, consider this situation. So this would still imply pH collapse, right? So just because sigma 2 not equals to pi 2 does not mean that pH cannot collapse, right? All it means is that pH cannot collapse to second level, right? But it can collapse to the third level or the fourth level or so on, right?
Yes,
So statement Q cannot be, like, need not be true, right?
yes. So in that sense,
Right.
yeah.
Yeah. In fact, okay, statement Q is not true.
Hmm.
Why? Because of this word implies.
Hmm. Correct.
Yeah. Okay, so yeah, let's look at this one. So suppose for that phi xy is true, where phi is some Boolean formula, then which of the following is correct? Uh, there exists y for all x, phi xy is necessarily true. There exists y for all x, phi xy is necessarily false. And there exists y for all x, phi xy may or may not be true, but neither is implied from the assumption. So which of these three is correct?
I think C is correct.
Yeah.
Yeah. Okay, so can you tell me why A is false?
Because for each x, there might be a different y that makes the
Yeah,
entire thing true.
right. So let I only okay. So then okay. So if phi x comma y equals 1 if and only if x equals to y, then the statement for all x there exists y, phi x y is true, right? Is this fine?
Yes.
Yeah. Uh, but the second statement is false because there does not exist any y which is equal to all x, right?
Yes.
So in particular, I cannot pick any y over here because then that y would have to be equal to all x, which is not possible, right? So that means A is false, right? Is this fine?
Yeah.
Okay, so now can you give me an example of a phi for which B is false? This is very simple.
It's the same y for which all x becomes true.
Can you repeat that? I did not
Uh,
understand.
for for all x, there exists a specific y which makes the thing true. So
Right.
then,
Yeah, yeah. Yeah, so what I'm saying is, okay, so these two are the same. Over here, we prove that there exists a phi for which this is not true. So can you now show me a phi for which this is false? That is, can you now show me a y for which there exists y for all x, phi xy is true?
phi of x1 is 1.
Yeah. So it's just this phi of x comma y is equal to 1. You just ignore x and y completely. So in that case, this would be true and this would be true. Because we are ignoring x and y, right? So is this fine? Okay, am I audible?
Can you explain this? It's not clear that if you simply write phi of xy is equal to 1,
Okay.
it shows that this is something which is true for all the x, for all
Yes.
x, and there exists some y for which this is true. And if we consider, yeah, so this is necessarily false. So for all x,
Okay. First of all,
there
this is
exists
true,
y
right?
is
For
true.
all x,
Yeah.
there exists y. Phi xy is true,
So yeah, necessarily false. So it is not it's not necessary. So there exists y.
right?
Uh,
So what I'm saying is, forget about y, forget about x. Phi xy is always 1, right? So
yes.
even if you consider some y,
Yes. So
it's still true,
it, it is still true.
right? So what we have shown is there exists a phi for
Mhm.
which this is not necessarily false, right?
Yes. Correct.
And that disproves two. That disproves B, right?
Mhm.
Yeah. And that's what we wanted to do, right?
Right.
Yeah. Okay, so it's 8, but we started 5 minutes late because of some technical issues. So yeah, let's do two more problems. I think we can finish these two. Okay. Yeah. So consider the following problem. A is the set of all triples GST, so that G is a directed graph and does not have a Hamiltonian path from S to T. So which of the below statements is known to be true? A is in P, A is in co-NP, A is co-NP complete. So which of these are true?
The last two, D and E, I think.
Okay. So G is a directed graph and does not have a Hamiltonian path from S to T. Suppose I were to remove this and say has a Hamiltonian path, then
So
B and
has
C would be true,
Hamiltonian
right?
path, then it would be in NP and then NP complete.
Right. So the complement of A is an NP and NP complete. So A is co-NP and co-NP complete. We saw this before, right? L is NP implies that L complement is co-NP. L is NP complete implies L complement is co-NP complete, right?
Yes.
Yeah. Okay. So is this fine? Then we can look at the next one. Yeah. Okay. We also need to show that these three are false. But okay, if A were in P, then P would be equal to co-NP, and A is in NP, NP and co-NP would be the same, which we don't know. And if N is co-NP, NP complete the same thing. Again, NP and co-NP would be the same. So this
Yeah, so the
implies P
complement of
equals to NP
complement of a
and
P would always be in P. Is it?
yeah. Yeah, so okay, that was one of the problems somewhere. Yeah, so that was one of the problems somewhere, but I don't think we'll get there. So yeah, but that statement is true. If L is in P, then L complement is also in P. So was that the question? Oh, okay. Okay, so what I was saying is, okay, let me write.
Are you asking about the next question? Because I could not hear you.
Yeah, so I am writing that in the chat. So were you asking this question?
Yes.
Okay, yeah. Yeah, so this is true, but so yeah, I won't have time to prove that. But the thing is, you for a deterministic algorithm, you can flip the output.
Yes.
Yeah. So that's the proof idea. Okay, so is this fine?
Yes. Yes.
Okay, so let's look at this one. This is going to the last problem. Suppose a language B is not in NP. Which of the following has to be true? B and B is sigma 2p or none of these. So which of these has to be true?
I
None
think
of
B,
these.
B and C, B and C are, oh, none of these.
It can't be
It's
B.
none
It
of these.
can't be B.
B is the
Okay.
element. If it is B is not in NP,
Okay, here's an example. So halt is not in NP, right? Halt is a halting problem,
correct. Yeah.
but it is not in P. It is not in co-NP. It is not in sigma 2p. But because if it were in any of these three, it would be decidable, right? But halt is semi-decidable.
Yes.
So there exist languages which are not in NP, but are neither in any of these.
Correct.
Okay, so I think let's end over here if there are no other questions.
So, what will be the topic of the next problem solving session?
So next is on 15th,
Hmm.
and by that time the deadline for both assignments 1 and 2 of this week, like this offering would have passed, right? So what we can do is we can first discuss some problems from week three's assignment from the last year and
Hmm.
week 1 and 2 assignments from this year.
Okay. Okay.
Yeah.
Okay.
But the problem is I don't think we'll have time to cover all of those.
Hmm.
So, okay, so if Okay, so if you have any preference for like assignment 1 or assignment 2 from this time, you can tell me now. Like I'll try to cover that.
Yeah, so it's okay that if we cover the assignment 2 at least.
Okay, so what we can do is first cover assignment 3 from last year and then cover assignment 2 from this year.
Yes,
Yeah.
it will.
Okay. So if there are no other questions, we can meet next.
Thank you so very
Yeah.
much. And
Yeah.
we faced lot many voice issues this time.
Yeah.
That's
So
great.
today was a mess. First,
Yeah.
my camera wasn't working. Then both of us lost, like almost all of us lost connection multiple times. Yeah. Let's
Thank you
hope
so
this does
much.
not happen next time.
Yeah. Thank you.
Thanks.
Yeah.
Bye. Good night.
Bye.